95%. Take a look around you. Everything you see, everything you've ever known, is just 5% of reality. The other 95% of our universe is completely missing. At least, that's the official story. Physicists call it dark matter and dark energy, invisible ingredients needed to make their equations work. But what if it's not missing? What if the mistake isn't in the cosmos, but in the rulebook we're using to measure it? Tonight, we put the universe itself on trial. Is reality filled with ghosts, or is the law of gravity simply wrong? Let's start with a crime scene, a spiral galaxy, much like our own Milky Way. Picture it as a gigantic, spinning merry-go-round made of hundreds of billions of stars. Newton's law of gravity, the same law that holds you in your chair, is the engine running this ride. And it makes a simple, ironclad prediction: the farther a star is from the galactic center, the weaker the gravitational pull, and the slower it must orbit. If it goes too fast, it gets flung off into the void. Simple. Except when we point our telescopes at distant galaxies, we see a universe breaking its own laws. The stars on the very outermost edge are moving just as fast as stars much closer to the center. It's like the horses on the absolute rim of the merry-go-round are keeping perfect pace with the ones near the hub. This should be impossible. The ride should be tearing itself apart. The galaxy should be disintegrating before our eyes. So what's going on? Detectives in this cosmic mystery have two main theories. Theory 1, the galaxy isn't what it seems. It must be surrounded by a massive, invisible halo of something. A dark matter scaffolding that provides the extra gravity needed to hold those speeding outer stars in their orbits. We can't see it, we can't touch it, but this theory says it must be there, outnumbering normal matter 5-1. The case for this unseen suspect is strong. Why? Because the clues keep piling up. Look at how giant galaxy clusters bend light. Einstein showed us that mass warps spacetime like a bowling ball on a trampoline. Light from a distant object has to follow that curve. When we look at huge clusters, they act like cosmic magnifying glasses, distorting background galaxies into strange, beautiful arcs. This is gravitational lensing. The amazing part? The amount of warping we see is way more than the visible stars and gas can account for. The lensing map tells us the bulk of the mass is an invisible cloud surrounding the entire cluster, exactly where dark matter is predicted to be. But the smoking gun, the one piece of evidence that seems impossible to argue with, is called the bullet cluster. This isn't one galaxy cluster, it's two that have smashed into each other at millions of miles per hour. It's a cosmic car crash of epic proportions. When they collided, the normal matter, the giant clouds of hot gas, slammed into each other and slowed down, creating a glowing, X-ray shockwave right in the middle. But when we map the mass using gravitational lensing, we find something shocking. The vast majority of the mass didn't slow down at all. It sailed right through the collision, like two ghosts passing through each other. We see two distinct clumps of mass that are completely separate from the glowing gas of normal matter. Mass and light have parted company. This is the cosmic equivalent of seeing footprints in the snow, with nobody there to make them. It's screaming that there is something real, massive, and invisible that doesn't interact with normal stuff. Case closed, right? Not so fast. Zoom out even further, to the entire observable universe. Our best computer simulations, when fed with the laws of physics plus a generous helping of cold dark matter, grow a universe that looks exactly like ours. A vast, spongy cosmic web of filaments, nodes, and voids. Without that invisible scaffolding, the simulated galaxies form too slowly and clump together in the wrong way. Then we look at the oldest light in existence, the cosmic microwave background, the afterglow of the Big Bang. It's a baby picture of the universe, and it's not perfectly smooth. There are tiny temperature ripples, frozen sound waves from that primordial soup. The pattern of those ripples, their size and spacing, acts like a cosmic DNA test. And that test comes back with a clear result. To create the patterns we see today, the early universe must have contained a huge amount of non-reacting, non-glowing, heavy stuff. Dark matter. 4 different scales, spinning galaxies, bent light, colliding clusters, and the baby universe, all pointing to the same invisible suspect. And we haven't even talked about the other 70%. This is where the story gets even stranger. In the late 1990s, astronomers were using a specific type of exploding star, a type I supernova, as standard candles. Think of them as cosmic light bulbs that always have the same wattage. By measuring how dim they appear, we can tell how far away they are and how fast the universe was expanding in the past. Everyone expected to find the expansion was slowing down due to gravity. Instead, they found the opposite. The distant supernovae were even dimmer than predicted, meaning they were farther away than they should be. The only way for that to happen is if the expansion of the universe is accelerating. Space itself is stretching apart, faster and faster every second. What could be doing that? What could be powerful enough to overpower the gravity of everything in the universe? Scientists gave this mysterious force a name, dark energy. It acts like a constant, repulsive pressure embedded in the fabric of space-time itself. It's the lambda in what scientists call the lambda CDM model, our standard model of cosmology. It's a chorus of evidence, from supernovae to the cosmic microwave background, all singing the same tune. A universe made of 5% normal matter, 25% dark matter, and 70% dark energy. A triumph of discovery. Or is it a colossal confession of ignorance? If your theory of everything only explains 5% of everything, how good is your theory? Here's where the defense gets its turn. The case for the dark universe, as strong as it seems, is starting to show cracks. First, if dark matter particles are real, we should be able to catch one. For decades, we built the most sensitive traps imaginable, vast tanks of hyperpure liquid xenon, buried deep underground in mineshafts to shield them from radiation. Experiments like XCNONNT and LZ wait in total silence, listening for the faintest ping of a dark matter particle, a WIMP, bumping into a xenon nucleus. The result after all these years? Utter deafening silence. Not a single, undisputed detection. We've tuned special radio cavities to listen for another suspect, the axion, converting into a tiny flicker of light in a magnetic field. We're still listening. We've looked everywhere. We've found nothing. Then there are the tensions. Measurements of the universe's current expansion rate, the Hubble constant or H0, don't agree. When we use our lambda CDM model to extrapolate from the baby picture of the universe, we get one number. But when we measure it directly using a distance ladder of nearby stars and galaxies, we get a different number. A higher number. It's not a small error. It's as if two impeccably built rulers are giving you different lengths for the same object. The discrepancy is growing, and no one knows why. Another tension, called S8, measures how clumpy matter is in the universe today. The standard model predicts a certain level of clumpiness. But some of our best surveys of deep space suggest the universe is a little bit smoother, a little less clumpy than it should be. The pancake batter isn't quite right. Why? These are cosmic scale problems. But the real headache for dark matter happens back at the scene of the first crime, individual galaxies. The theory that works so well on large scales has some serious neighborhood beefs. Simulations predict that dark matter should pile up into a steep cusp at the center of galaxies. But many real dwarf galaxies show a much flatter core. Dark matter theory predicted thousands of tiny satellite galaxies swarming our Milky Way. For years, we couldn't find them. We're finding more now, but the numbers game is still tense. The standard model, for all its power, feels clumsy on these smaller scales. And amidst all this, an elegant, almost magical observation has emerged. It's called the radial acceleration relation. Forget dark matter for a second. It turns out if you just look at the visible matter in a galaxy, the stars and the gas, you can predict the exact rotational speed of its outer stars with breathtaking precision. It's a single, universal rule that works for thousands of different galaxies. This is deeply weird. It's like discovering you can predict the traffic flow of every city on Earth just by looking at the map of their streetlights, without needing to know anything about the cars. In a dark matter universe, this tight relationship is a bizarre coincidence, requiring the amount of visible matter and the shape of the invisible halo to be perfectly, mysteriously coordinated every single time. Is it a coincidence? Or is it a clue? A giant, flashing arrow pointing away from extra ingredients, and towards a new rulebook. Towards modified gravity. This is theory 2. No ghosts. No invisible scaffolding. Just a simple, radical idea. Maybe Newton and Einstein were right, but incomplete. This theory, in its most famous form, is called MOND, for modified Newtonian dynamics. It proposes that gravity doesn't get weaker in the way we expect. MOND says that below a certain, tiny level of acceleration, about a 10 billionth of AG, gravity gets stronger than Newton's law predicts. It just doesn't fade away as quickly. On Earth, or in our solar system where accelerations are high, you'd never notice the difference. But in the vast, empty suburbs of a galaxy, where acceleration is incredibly weak, this stronger gravity takes over. And with that one simple tweak, no new particles, no dark stuff, galaxy rotation curves snap into perfect focus. The merry-go-round suddenly makes sense. The weirdly tight acceleration relation isn't a coincidence anymore, it's the direct consequence of this new law. It is breathtakingly economical. So, have we solved it? No. Because for every problem MOND solves in a galaxy, it creates a new one somewhere else. On its own, classic MOND can't explain the extra mass we see in galaxy clusters. And it utterly fails to explain the bullet cluster, where the mass and the visible matter are in two different places. It also has a really hard time matching the precise pattern of ripples in the cosmic microwave background. So theorists got creative. They built relativistic versions of MOND, like Tevis, F, R, gravity, and dozens of others. They add new fields and forces to spacetime to try and make it work on all scales. Some theories even suggest gravity isn't fundamental at all, but an emergent property like temperature, arising from deeper quantum information. But the more you patch a theory to fit the data, the more it starts to look like the complex theory you were trying to replace. The beautiful simplicity starts to fade. So here we are, at the final audit. Two competing paradigms. On one side, lambda CDM, a universe filled with two mysterious, invisible substances that have never been directly detected, but which brilliantly explain the universe on the largest scales, despite some nagging tensions and local problems. On the other side, modified gravity, an elegant idea that solves galaxy-scale mysteries with stunning simplicity, but which struggles on cosmic scales and requires increasingly complex extensions to stay in the game. It fixes the local crime scene but can't seem to account for the city-wide conspiracy. The implications of this choice are profound. If dark matter and energy are real, it just continues a long tradition in physics of discovering hidden layers of reality, atoms under chemistry, quarks inside protons. It would mean most of reality is a new kind of matter, waiting for a new kind of physics to describe it. A lawful, but deeply strange universe. But if gravity is wrong, it's a much deeper revolution. It means the very fabric of spacetime, our understanding of space, time, and mass for over a century, is just a local approximation. It suggests that the map we've been using to navigate reality is missing a continent. The next few years will be decisive. Fleets of new telescopes are coming online. Euclid is mapping billions of galaxies. The Roman Space Telescope will make our pictures of dark matter halos razor sharp. The Rubin Observatory will create a high-definition movie of the night sky. They are designed specifically to stress test these two models until one of them breaks. The audit isn't over. The numbers are still coming in. So, the cosmic ledger is on your desk. The evidence is in front of you. Based on what you've heard, where does your gut feeling land? Are we living in a universe filled with an invisible scaffolding that makes up 95% of everything? Or are we just using a broken ruler, misreading the fundamental laws of nature? Let me know in the comments. Are you on Team Dark Matter or Team New Gravity? There's no wrong answer, just a fantastic debate about the nature of reality itself. And if you think this cosmic mystery is deep, you won't believe where the evidence took us when we audited the very fabric of time itself. That investigation is queued up for you right on the screen. To make sure you never miss an audit and always get the unfiltered truth about our universe, smash that subscribe button and ring the bell. We do this every single day, because the truth is out there, waiting to be found.